Yeah, what does a magnetic field do? This could be really horrible, right? I could be writing some giant integral up here. But unlike everything else in the class, the universe was nice to us. So it's the torque. Tau will be torque of magnetic field on a magnetic dipole. Okay, so the torque is the dipole across the field. Is that awesome? All right, so I know that the torque part of UP1 is nobody's favorite part, so I need to redefine what torque is for you guys. So torque torque is going to be sum of a displacement from some pivot point to the point where the force is applied. So P is a pivot point. And I is the point the force is applied. Let me draw a rock. So this is a non-magnetic rock. So back mechanics, no magnetism, no electricity, just a rock. And somehow I'm going to drill a hole in a rock. Cool. So it rotates about that point. I'm going to pull on it, maybe in that direction. So this will be the point Ri. Here's the force. There's displacement from the pivot to the force point. And if there's only one force, the torque is, how am I getting that backwards? Is that displacement vector from the pivot point to the force point crossed with the force. And let's say we can do that cross product. This is R cross F, gives me torque in the board. Now we need to know what that means. Another right-hand rule. This is the right-hand rule of torque. Point thumb toward the torque. The fingers curl. The fingers curl towards the angular acceleration. That's the last time we'd say angular acceleration. So generally when we're looking at torque, we'll put a torque on something and see which way it rotates. So the angular acceleration will be the same direction as the initial rotation. So the fingers curl toward the direction of the angular acceleration. Which is the direction of the initial rotation. All right, so let's try it out. So I point my thumb towards the torque. My fingers curl like this, so initially the rock's going to rotate this way, which based on your intuition of what that force would do, is exactly the direction the rock's going to rotate. Okay, so we hauled this into your lab. Did we? Well, we will haul this into your lab. So what we've got is some coils. Oh, we did haul it in. It's a problem with giving the lecture before I give the lab each week. So what we've got is some PVC pipe, and we wound some wire on it. We're going to put one in our lab magnet. Then we ran some current through it, and the coil would spin in your hand. You could turn it away from equilibrium and spin back, which is part of the electric motor. We call these a torque coil. So this is my magnet again, north, south. Here's my pipe. And we wound about 20 turns, I'd say, of wire on it. So that it fit in the magnet. Here's the field. So the moment there is into the board. I get the same direction as my notes. Yep. And so let's see, the torque will be M cross B. The torque will be down. The torque will be this way. And so grab the thing with the right hand, this thing's going to rotate in that direction. So let's figure out how much. So we need some parameters. This was, the width of the coil was 7 centimeters. The length of the coil is 7 centimeters. The width, about 1 centimeter. B is 0.2 Tesla again. And I think I'm running the 2 amp batteries again. So the moment is the field times the current times the area. Is the field times the current times the length times the width. 20 turns, 2 amps, 0.07 meters, 0.01 meters is 0.028 amps meters squared. And then at this geometry, I've drawn it at an orientation where the moment and the field are at right angles. So the torque, or the magnitude of the torque here, is the magnitude of M cross B. It's just MB, because once again, sine of 90 is 0. Sine of 90 is 1. So this is just 0.028 amp meters squared, 0.2 Tesla, 0.0056 Newton meters, believe it or not. And you'll have to work on canceling that down. So, definitely observable, not very big. All right, something we're not going to do a ton with, that you guys should be aware of, particularly those people going on to do quantum mechanics eventually. Since, if we take a dipole moment, it wants to be in a certain direction, we exert a torque to move it away from that direction. Causing that rotation, we have to, we put energy in the system. So this is the potential energy. Dipole. It's just U equals minus M dot B. And for the folks taking quantum mechanics, that'll be important because electrons do have magnetic dipole moments, and one of the easiest ways to control them is put them in a magnetic field. Okay, so spinning back a few lectures, a few boards, I said that the magnetic force on a dipole in a uniform field is 0. But we've been observing net magnetic forces all over the place, right? I mean, you guys just snap my magnets together all the time in labs. So if their magnets are snapping together, they're experiencing that force. So it can't be, it's got to be the non-uniform field that's producing the force. And so we need to figure out something about that at least, because it's our primary observation with magnets. They stick to refrigerators. Okay, so just to recall this, so a uniform field there's zero net force on a dipole. Actually, this is true for electric fields and electric dipoles and magnetic fields and magnetic dipole, which means net force requires a non-uniform field. That means any you go planning to build coil launchers, rail guns, etc. Well, rail guns actually complicated because the rail gun involves an electric field that's hard to find. But for a coil gun, you're not going to launch something with a solenoid that has a nice uniform field. So you have to work on producing a non-uniform field. So I'd like you to recall what you already know about forces. So let's take some magnets. Whoops. You know that north attracts south. So opposite poles attract. You know that north repels north and south repels south. Like poles repel. So we're going to use that to figure out the direction of force on a dipole. So I'm going to put a dipole in a non-uniform field. Let's see, let's do this. It's a nice non-uniform field. And here's the natural orientation for a dipole. It wants to have its moment aligned with that field. So if the moment is aligned with the field, in the same direction, force is towards stronger field. All right, the field's stronger here, so this will feel a force that way. Which is unfortunate. If you want to shoot something, you like to push it out of the field. But the most natural orientation is to have the thing sucked into the field. Now, that's kind of a convoluted rule. So, in general, to figure these things out, I just put in a magnet that could have produced that field. So this field could have been produced by a magnet that looked like that, with a south pole here, a north pole here, and then you can clearly see that this north pole would attract that south pole. All right, the other case is we get the moment pointing in the opposite direction of the field, which I'm going to have to restrain it somehow because it want to spin around. Let's clean the picture up. So now I'm going to take my same non-uniform field. And now the moments will have to point the other way. And like I said, if we just set this up, the thing would immediately start rotating. So we'd have to put it in a tube or something, which is what we actually do when we use this. So a moment in the same direction of the field, a moment opposite direction of the field, sorry. The force is towards weaker field. Force on this thing would be this way, which is what you want to do. So, and this effect is exactly why, if you've ever done this, you get some of those annular magnets, circular magnets, and you stack them on a pencil. And if you want them to float, you have to keep flipping the poles so that you get the moment anti-aligned with the field or opposite direction of the field at each point. And we can do the same trick with our magnets. So, same magnet that can produce the field. Now north repels north, and we get a repulsive force.